Watch this video, I don't know what happened. My recorder shut halfway through, so the beginning part of this lesson will just be a mystery that you had to have been here for. I'll find my recording from last year. But aside from combustion reactions, which realistically were not something that was a big shock because we had talked about those already, we have addition reactions. These are different and new. It's not a type of reaction that you've talked about before. In an addition reaction, any unsaturated hydrocarbon can react with something that is small. It has to be unsaturated because we need that double bond or the triple bond for the reaction to work. What's realistically happening is that wherever the carbons that are part of the double or triple bond are, that's where we're going to add this small molecule. Now, what are the products of an addition reaction? It's dependent on the type. So there's more than one possible outcome of an addition reaction, and I'll show you a few of the most basic outcomes. What kind of small molecule can it be? Well, it's typically hydrogen, water, some sort of compound with a halogen in it. Sometimes it'll be hydrogen and a halogen, so something that could be an acid or maybe is an acid. Or X2, so like F2, Cl2, Br2. Anytime there's an X, we would replace that with one of the halogens. So I'm just going to show you a few of these examples so that you can see what it would look like if we were doing an addition reaction here. Now, if we're adding hydrogen, an addition reaction would produce an alkane. So what would that look like? Well, there would be some carbons with a double bond. What's on either side of them? Whatever. We're only focusing on the ones that have the double bond because that's where all the action is happening. We're going to add hydrogen. Now I'm specifically drawing both hydrogen atoms out so that I can show you where they go. One of the hydrogen atoms will attach to one of the carbons that's part of the double bond, the other hydrogen to the other one. Is there a rule about which one goes where? No. So I drew them this way because that looked nice with the arrows. That's really all. Because they're both hydrogen atoms, I could do this or I could reverse it and put the first hydrogen on the second carbon, but I would end up with the same outcome. So when I'm doing this, what do I get overall? Well, I get two carbons that are connected by a single bond. They each have whatever was attached to them before, plus this extra hydrogen that I just attached to each of them. So in an addition reaction, the common thing that will happen is that there will have been a double bond. The double bond will get broken so that we can add another atom to each carbon that was part of the double bond. So if we look at a real example of this happening, one of the things that you might be expected to do is to predict what the product will be. And not just in general, it'll be an alkane, but specifically what would the name of the product be. So if I take but2ene, so that would be 4 carbons with a double bond between carbon 2 and carbon 3. That means there are 3 hydrogens here, 1 here, 1 here, and 3 over there. So that's my but2ene. I'm going to add hydrogen, which I'll just represent as 2 H's. One of the hydrogen atoms will go and attach to one of the carbons that was in the double bond, and the other hydrogen atom will go and attach itself to the carbon on the other side of the double bond. What do I get? I get this. So if I had to give that a name, what would I be calling it? Butane. So, name all possible products. The only possible product of this reaction is butane. Now, the reason it says name all possible products is because there will be some scenarios where there might be more than one thing that we could produce, but not in the case of adding hydrogen. Because I'm adding two identical atoms, doesn't matter which way I add them, I'm going to get the same product. Now, does anyone have any questions about this? So that's what it looks like if I'm adding hydrogen. Another small molecule that I could add could be a halogen. So if I'm adding a halogen, I'm going to take my double bond and I'm going to add whatever the halogen is. I'll just represent it with X's here. Same thing, one of them will go on one side, the other will go on the other side, so that in the end, I have carbons attached with a single bond. They still have whatever they had attached to them, but now they have two atoms of whatever halogen it was. Now this is slightly different. It looks the same as adding hydrogen, but when I go to name a compound, if the thing I'm attaching isn't hydrogen, it's going to change the way I name the compound. So if we take a look at a specific example, we'll take cyclopentene, and I'm just going to represent all of the carbons here so we can see them. If it were a regular line diagram for something that was cyclic, you wouldn't necessarily have to, but I just want us to see them. I'm going to put my double bond there because I can. When things are cyclic, wherever the double bond is, you assume that's carbon 1 and carbon 2. If I'm looking at hydrogens here, the ones part of the double bond have one hydrogen, and the ones that aren't have two. Now I'm going to add chlorine. Chlorine is Cl2. And I'll do the same thing I did for hydrogen, represent the bond that's between the two atoms of chlorine. Now we'll represent each atom attaching itself to one of the carbons that was part of the double bond. And the thing that's different here is that instead of just getting a plain old alkane, I'm going to have an alkane with halogen side groups, so I'm going to have to name them. So what will I have? I'll still have my cyclic structure based on 5 carbons. But instead of the double bond, I'm going to have the chlorine atom attached on each of those carbons. So when I go to name this, I would have to call this 1, 2 dichlorocyclopentane. So instead of just getting an alkane, I get an alkyl halide where I have halogen atoms attached. And remember, halogen atoms work the same way a side group does. They're part of the prefix. Now, is there more than one product that's possible here? Or is this the only thing I could make? Would it matter which carbon I attached each chlorine atom to? No. Because I'm attaching two identical atoms, I'm going to get this as my product no matter what, because even if I switch where the chlorines go, that is still how my structure would look, and that's still what I would call it. Yes, Danny. You would not. One of them has to go on each of them. In any addition reaction, one of the carbons that's part of the double bond gets one atom, the other gets the other atom. Now there are other scenarios possible. One of them involves a test that gets used in the lab to detect whether or not something is saturated. This particular thing, this bromine test, it got its own curriculum outcome. What does that mean? that there could be, and usually is, specifically a question about using bromine as a test. We can use bromine as part of a simple addition reaction to determine saturation. That's what we're trying to do. Remember, a saturated compound only has single bonds. An unsaturated one has double or triple bonds, or something that's not a single bond. Now, Br2 aqueous is this brown, sort of orangey brown colored solution. I'm going to add the word orange here because they really play it fast and loose with what color they say bromine actually is. Is it brown? Is it orange? Is it brownish orange? It has a color. It's not a very pretty color either. If we add bromine to a sample that we have and it participates in an addition reaction, the brown color disappears. So, if bromine actually participates in a reaction, so if there was a double bond that could have been broken and bromine could be added, then the brown color disappears. So just as an example of how that would look, if I compare Pent2ene and pentane, both in a reaction with bromine. Pent2ene, is that saturated or unsaturated? Well, hopefully you look and you're like, ooh, alkene, unsaturated, it has a double bond. So when I add that Br2, something different should happen than when I have pentane. Now if I have pentene, Pent2ene, and I add bromine, Pent2ene, if we draw it very briefly, that's Pent2ene. I could add an atom of bromine to each carbon that was part of the double bond. So in the end, instead of having Pent2ene and bromine, I'm only going to have one thing. I'm going to have this compound, where I've taken away the double bond and added an atom of bromine to the second and to the third carbon. I would call this 2,3 dibromopentane. And that's it. That's the only product of this reaction. If I have pentane and Br2, I will have pentane and Br2 still at the end. It's not going to participate in a spontaneous reaction because there was no double bond for it to react with. So let's take a look. This is brown. This is brown. This is brown. So if there was an addition reaction, I went from having a brown liquid to having no brown liquid. The color disappeared. If the compound was saturated and there was no addition reaction, the brown color stays. It would be very, very probable for the bromine test to be part of a question. Usually the question is, what color change would you see, and what was the structure of the compound that was in the question, or something to that effect. But I would predict that there would be a question about this test. Does anyone want to ask anything there? Now we can also add something that has two non-identical atoms. If we add a hydrogen halide, we are taking our double bond and we are adding this. Instead of two identical hydrogen atoms or two identical halogen atoms, we're going to add one of each. Now, does it matter whether I add them like this or like this. Probably. There might be some cases where, because I have a small molecule, maybe I get the same name either way, but chances are the name of my compound might end up being different depending on where I add things. It won't always happen, but now I'm adding non-identical atoms, so it very much could. So that's what my point there is. Because non-identical atoms are being added, two different isomers may be formed. They won't always, but you at least need to consider that it might happen. Now, if I consider this reaction where I'm taking but2ene, and we already had but2ene in another question, but I'll just draw it here. There's but2ene. I'm going to add hydrogen chloride, so that's HCl. So I could put the hydrogen here and the chlorine here, or I could put the hydrogen here and the chlorine here. Now I'm just going to draw what I would get in both of those scenarios so that you can see. If I do what's on the top and I add the hydrogen to the first one, I get this compound where the chlorine is attached right there. If I do what's in green, I get this. And you might think, ooh, that's not the same. That doesn't look the same. I didn't draw it the same way. Those must be two different isomers. So think about what you would name each of them. You find the longest chain, 4, butane. Then you start numbering carbons so that functional groups or side chains, whichever one applies, have the lowest number. I would call both of these compounds 2-chlorobutane, because I would number the carbons 1, 2, 3, 4, or 1, 2, 3, 4. So in this case, because my molecule was small and the double bond was precisely in the middle like that, I actually end up calling both options the same thing. Now that's what happened with but2ene. The next example is what would happen with pent2ine. And now, because we have an uneven number of carbons, you'll see that there's more than one potential outcome. Does anyone want to ask any questions about this example before we do the next one? So in this one, we have our pent. Now this time we have a triple bond. So there's actually a couple of scenarios for what can happen when you have a triple bond. It's possible that we have a limited amount of the other compound. So we have our hydrogen bromide. If we only have a little bit of it, we might not be able to completely break the triple bond. So we could have a product that still has a double bond in it, or we could have products that have single bonds, depending on how much of this other substance we add. So there are lots of possibilities for what kind of products I could get. Let's consider just what would happen if I was left with a compound that has double bonds. That way we can depict just one atom of each type being added onto the structure. So if this is the scenario we go with, Our hydrogen could be added here and bromine here, or hydrogen could be added here and bromine here. So we have two different possibilities for where we're adding things. And I'd like for you to take a minute and see if you can come up with the name of the product. So we're just going to break the triple bond into a double bond. And there are two potential products that we could have. One if we do what's in green, and one if we do what's in red. So if we follow the path that's in green, that's on the top, I'd be adding hydrogen to the third carbon and bromine to the second carbon. This one would end up giving me, oh, I should use the right color, 2-bromo-pent-2-ene. Because my bromine would be on the second carbon and the double bond that would be left over would be between the second and third carbon. If I did what was in red here, now I'm adding bromine to the third carbon. That would be 3-bromo-pent-2-ene, because now I would have added my bromine atom to a different carbon. And because the double bond is also there, I would have to name it something different. I would have named it something different in both scenarios. But generally, when you have an odd number of carbons in the chain, there's more than one isomer you can form, depending on where your things are attached. Now, there is one more example where we add water and produce an alcohol, but I think that we will